Okay, so now we're going to look at the discrete equations that I had. So I have a mass matrix times the second derivative of my nodal degrees of freedom is equal to my external forces minus my internal forces. So how do I solve this? This is still a function of time. Computers don't do continuous functions very well. And so what I need to do is I need to define a time step, an integration scheme to discretize in time. And what we use is something called the leapfrog scheme. And so I'm going to draw on an axis. Here's the time axis. I'm going to draw steps t, t plus delta t, and t plus 2 delta t. So that's my axis in time, with discrete steps in time. And then at halfway, I have t plus delta t over 2 and t plus 3 delta t over 2. So those are my half steps in time. And so what I'm going to say is I'm going to keep track of my d coordinates. So the way I'm going to write this is d is my displacement, and I'm going to write it in terms of the time step n. So d sub n, here I have, at the next time step I'll have d sub n plus 1. At the next time step I'll have d sub n plus 2. I'm also going to calculate my accelerations. So d double dot at n, d double dot at n plus 1, and d double dot at n plus 2. And then at the half steps, I'm going to keep track of the velocity. So v at n plus 1 half, and here I'm going to have v at n plus 3 halves. Okay, so those are the different, I'm going to have the accelerations and the displacements at the time step, and the velocities at the half time step. And this lets me use a second order accurate, which means the accuracy is proportional to my time step squared, integration rule based on a central difference. And so basically I can say that my acceleration at a time, so d at n plus 1 double dot, is going to be equal to v at n plus 3 halves minus v at n plus 1 half divided by delta t. So I'm taking the difference between these 2 points, the time span between t plus delta t over 2 and t plus 3 delta t over 2 is just delta t. And so I take a central difference in time of the velocities like this. And so then I can also write that v of n plus 1 half is equal to d of n plus 1 minus d sub n over delta t. And so here I'm taking a central difference from step 1 to 2 to get v at the half step. And so the approach that I'm going to use is, given a step in time, I'm going to update the velocity using the acceleration. Having the velocity, I'm going to update the displacement at the next step in time. And so this algorithm is called the leapfrog algorithm. So I update displacement a step, and I update velocity a step, and because they're half off of a step from each other, they're always jumping over the other one. And so let me write out really quickly what the algorithm is. And so the algorithm has 4 steps, or 5 steps. And so the first thing that we would need to do is set our initial conditions. And so the initial conditions that have to be set are, we have to set the velocity, v sub 0. We have to set the initial coordinates, d sub 0. So this is, let's write it all in terms of d. So d dot sub 0 and d sub 0, so you have to set the initial velocity and the initial position, and we compute the mass matrix M. Remember, the mass matrix was just integral of shape function, so it's constant as a function of time. The second step is to compute the forces. F external minus F internal, using the integral equations that we had before. And so this gives us our right-hand side. We could just call this F. And this is F at time n, because we're using, in the first step this will be at 0, at the next step it'll be whatever step it might be. So this is at the current time step. From this, then we can compute the acceleration. So d double dot at time step n is equal to the inverse of the mass matrix times F, in this case J at n. Now, of course, we don't actually compute the inverse of the mass matrix. We solve a linear system of equations, but that's the way that we write it. Step 4 is we will compute nodal velocity, or update nodal velocity. And so here, we're basically just going to take, we know d sub n, so we have to shift this. So we know d sub n, we know v sub the last step, and so we solve for the next step. And so the equation for this is that v sub n plus a half is equal to v sub n minus 1/2 plus d double dot of n times delta t. So you can see we're just taking this time derivative is the well, let's fix this. So instead of v, we'll use d dot. So we have the derivative at the half time step. We're using the acceleration at the current time step, which updates to the derivative or the velocity at the next half step. And the last step of this is to update the nodal coordinates. And here we have d of n plus 1 is equal to d of n plus v at n plus 1/2 times delta t. So that's the second leapfrog. So the first step is to bring the accelerations up. The second step is to bring the displacements up. On the very first step, we don't actually probably have the velocity, but you could do two things. You could either pretend you know the velocity at the half step before you started, or if in the first step this is actually just going to be v sub 0, and so you just take 1/2 the time step. It's not second order accurate, so there's some issue with that, but that's a typical way to do it. Okay, so the last thing to talk about is how do we make this not so expensive? Because once we do this, then we go back to step 2. And we repeat doing that until we've simulated the amount of time that we want to simulate. And so none of these things the only thing that involves solving a system of equations is this step. And so to make that step faster, we often do something called mass lumping. And mass lumping is we take Mij and we sum each row. So we take all the values on a row, we sum them up, and we put that value just on the diagonal. So basically we say Mij summed on j gives us Mi. So this becomes more like a vector term. And so that gives us a diagonal matrix on Mi, which then computing the inverse of is just as simple as just taking 1 over each of the components of the diagonal. So we'll talk more about this in the next class, but this gets you started with how we solve explicit or dynamic problems with finite elements.